F block elements, also known as inner transition elements. These consist of two series named as lanthanoids. These 14 elements with filling of 4f orbital and followed by lanthanium. Next is actanoids. The 14 elements with the filling of 5f orbital following actinium. But we have to understand, practically studying the actanoids is difficult compared to lanthanoids. Reason is, first, they are radioactive, meaning they decay. So safety is one problem, and decay, because of decay, chemistry will change. Second, there is occurrence of a wide range of oxidation state for these elements. So let's first see these two series. Lanthanoid series start with lanthanum, 58 cerium, presmodium, praseodymium, neodymium, promethium, samarium 62, europium 63, gadolinium 64, terbium 65, 66, dysprosium, holmium 67, iridium ER at 68, thulium 69, ytterbium 70, lutetium 71. So these are lanthanoids from 57 to 71, actanoids from 89 to 103, like actinium, 90 is thorium, protactinium, 92 uranium, one among the most important element in the actanoids, neptunium 93, plutonium 94, americium 95, curium 96, brachylium 97, californium 98, einsteinium 99, fermium 100, molybdenum 101, nobelum 102, lawrencium 103. So here we see the names are after certain scientists and cities. These are actanoids. First, lanthanoid. Electronic configuration of lanthanoids are with 6s2 common, but 4f orbital is variable in them, starting with lanthanum. Atomic and ionic sizes in lanthanoids. There will be a systematic decrease in the atomic and ionic radii, right from lanthanum to lutetium. This is known as lanthanoid contraction. We will study the 3 positive or trivalent oxidation state of all the elements in lanthanoids, right from lanthanum to lutetium, because 3 positive is the most characteristic oxidation state. And we will see the ionic radii systematically decreases, linearly decreases along the series from 57 to 71. But there are a few other oxidation states as well, like cerium and presmodium, that do show +4 oxidation state. Samarium and europium too show 2 positive oxidation states at stable, having a TM and ytterbium 2 positive oxidation states. This linear decrease in ionic radii down the series is known as lanthanoid contraction. The reason is, imperfect shielding of 4f electrons, which is further lower than the d electrons. So the effective nuclear charge experienced by the valence electrons or outermost electrons in lanthanoids is greater than experienced by d block elements. So that is the reason with every unit of increase in nuclear charge with increase in atomic number, we saw a systematic decrease in atomic or ionic radii. This is the reason for systematic reduction in 4f series ionic size. Now let's see cesium 4 positive formation. The main reason for its formation is the extra stability that we will see with empty 4f orbit. That is the reason for the formation of 4 positive oxidation state for cerium. 3 positive is characteristic for all these elements. Plasmodium 2 also show 4 plus oxidation state. Now 2 positive oxidation states. Let's see. Europium 2 positive is formed by losing 2 s electrons, and we have half-filled F7 configuration with the formation of europium 2 positive. This half-filled electronic configuration that provides the extra stability is the reason that stable europium 2 positive oxidation state do exist. But for samarium, we have in 4f6, 1 electron short of half-filled oxidation state. Similarly, ytterbium will have a fully filled f orbital. That is the reason for the stability of ytterbium 2 positive. Color in the lanthanoids. Many trivalent lanthanoid compounds are colored both in the solid as well as in the aqueous solutions. Color of these ions may be attributed to the presence of F electrons. Let's see. Starting with lanthanum, which don't have any electron for excitation, it's colorless. Cerium 3 positive with single electron in 4f orbital, it's again colorless. And we see colorful compounds right from plasmodium to gadolinium. Gadolinium is again colorless because in 3 positive oxidation state it having a fully filled, half-filled electronic configuration, and that provides extra stability, and transitions are not that easy. We see colorful compounds from the lanthanoids, but except lanthanum and lutetium 3 positive. In many few compounds we see the absorption bands are narrow because of oxidation within the F level. Here we see from lutetium to gadolinium, what we see that again near 14 and 13 electron in 4f orbitals, they are colorless. like we having a lanthanum and cerium colorless with 0 and 1 are the electrons. Magnetic properties of F block elements. Lanthanoids except F naught type like lanthanum 3 positive and cerium 4 positive. And F14 we have a fully filled F orbital like ytterbium 2 positive, then lutetium 3 positive. Rest of the lanthanoids are paramagnetic, means they having unpaired electrons. That we already saw in case of D block elements. Magnetic lines passes through the material. What we saw in F block elements lanthanoids, paramagnetism is maximum for neodymium. Although neodymium doesn't have maximum unpaired electrons. The reason is there is this point like magnetic moment depends on both orbital as well as angular momentum from orbitals. So here is the interaction between both orbital as well as spin angular momentum, which was not the case for D block elements. That is the reason only unpaired electrons is not the concept to drive magnetic properties of our lanthanoids. For the same reason, neodymium having a higher magnetism compared to other elements in lanthanoid series. Now, standard reduction potential or standard electrode potential for the lanthanoid elements is vary from -2.2 to -2.4 except europium, which is -2. Now let's have a look at the certain chemical reactions of lanthanoids. First is oxidation. We getting a lanthanoid trioxide. Uniformly we get the same stable compound. Next is reaction with acids. Because of their negative standard reduction potential or standard electrode potential, they liberate hydrogen from acids. With sulfur, if we heat, we getting sulfides, 3 positive oxidation state. With nitrogen, we get lanthanoid nitrides. They having a electrode potential strong enough to reduce the nitrogen. So heated with nitrides. With carbon, we getting a carbides. With water, we getting a hydroxides, they are alkaline in nature. And halogen, we getting a trihalides compounds from lanthanoids. This is a general concept because there is such a similarity in their chemistry that almost we can show that in trivalent state, right from lanthanum to lutetium, chemistry will approximately remain the same. And same is the reason the purification of lanthanoid is not that easy because of such a similarity in their chemical properties. Next series is actanoid. all the actanoids having electronic configuration 7s2 with variable 5f and 6d subshells. Important properties to remember: actanoids are radioactive, meaning they will decay through alpha beta particles and move down the series or move up the series. Before we'll delve deeper into the actanoids, you see this is nothing but our rover gone on Mars mission. This mission was powered not by solar, as you can see here. There is no solar cells, but at the back one is a power backup, which is not a conventional power generator which stores energy, but it automatically generates it. It is known as a radiothermal generator, RTG. How it produces energy? It having a radioactive element that decays and produces heat. Using thermocouples, that heat can be converted back into electric potential. Using that, all the instruments on this rover was powered. So this is one of the great applications, even in the dark areas where there is no sunlight. Radioactive elements were used to produce electricity and power the missions. Now let's go add in these actanoids. Like lanthanoids, there is a gradual decrease in the size of the 3 positive or trivalent ions across the actanoid series. This is called a actanoid contraction, just like lanthanoid contraction. This is similar, but contraction is greater and there is a variation in that compared to lanthanoids. The reason is the same. 5f orbitals having a poor shielding effect, and they are more diffused than 4f. Looking at the electronic configuration of these elements, in neutral state, ground state, actinium having a D1 7s2 89, thorium will having a 6d2 7s2, so still there is no feeling of 5f orbital. We having a 5f 6d1 7s2, protactinium, uranium 5f3 6d1 7s2, neptunium 5f4 6d1 7s2, then plutonium 5f6 7s2. Somehow the d electron is shifted to f orbital. Plutonium, so it's important, 5f6 7s2. Neptunium, it is 5f4 6d1 7s2. Americium 5f7 7s2, and so on. But remember, uranium 5f3 6d1 7s2 92. In the trivalent state, what happens? It loses both S and D. So we are getting all the electrons left in f orbital. Here we see atomic radii. O3 positive, it consistently reduces, but not uniformly. For tetravalent, the reduction is still different. Now the maximum oxidation states increases from +4 thorium to +5, 6 and 7 respectively for protactinium, uranium and neptunium. But after that it starts decreasing again. That depends upon the number of electrons unpaired available in the F6d or 5s2 orbitals. 3 is uniformly existing for all these elements, just like we saw in case of lanthanoids. But remember, thorium don't show a 3 positive oxidation state. It's a curious point to remember. The reason is, for thorium, it having only 4 valence electrons. So thorium dioxide will be more stable than thorium 3 plus positive oxidation state. And we just know for uranium we have a 6 positive oxidation state. Uranyl ion, this is among the most important uranium compounds.